Good evening, everyone, and welcome to the Salon, live in Dementia Researcher Communities. Of course, available on our website and in our app as well, on the Apple and Google Play Store. I'm Adam Smith. I'm the Program Director for Dementia Researcher, and I'm your Salon host. Today, I don't always want to be the Salon host, so if anybody watching would like to host a future session, you're very welcome to get in touch with me, and you can take a turn in the hot seat. No hints there, Rebecca and Shea, if you'd like to. And you get a T-shirt. That's where I can say it. Rebecca's not wearing hers,
I've got mine.
despite my going to great efforts to send it away. But there you go. You get a T-shirt if you host. Well, thank you very much to everyone who's watching and dragged themselves away from the football. I promise, as I said, I will keep you updated on the scoreline. But let's get down to business. Today, we are excited to be going on to explore the critical topic of reproducibility in scientific research. Reproducibility is the cornerstone of scientific integrity, ensuring that findings are reliable, valid, and trustworthy. It plays a crucial role in building confidence in science and promoting the steady accumulation of knowledge. However, despite its importance, the scientific community faces significant challenges in maintaining reproducibility. I'm going to get stuck over that word a few times today, I suspect. I've spelt it wrong several times as well. I have to keep back and correcting it. Are we, as researchers, doing enough to ensure our experiments can be replicated? Will funders support these efforts? What factors contribute to the reproducibility crisis, and how can we address them? To help explore these questions, we have two brilliant guest speakers. We have Dr. Shea Andrews, who's a genetic epidemiologist whose work focuses on Alzheimer's disease. The Andrews Lab investigates the causal pathways of Alzheimer's disease and related dementias, employing statistical, genetic, and epidemiological approaches to large data sets. There are a lot of big words in there. Their research includes identifying causal risk factors, exploring mitochondrial genomics, and evaluating ancestry-specific effects of genetic variants on Alzheimer's disease. Did I get that right, Shea?
Yeah, no, that sounds pretty good.
Next, we have Rebbeca Williams, a PhD student at the University of Cambridge. Rebbeca completed her undergrad and master's at the University of Oxford, and then, for some unbeknown reason, went to the wrong place. I say that because I'm in Oxford. And now she researches fronto-temporal dementia and apathy. Her work is pushing the boundaries of understanding these conditions, I think it's fair to say. And Rebbeca is also a brilliant dementia researcher, blogger who writes for us every month in a very engaging, unique style. I love Rebecca's blog, so if you'd like to explore those, I'm going to post a link in the show notes when we get going. Hello, both. Thank you for joining and taking time out. So our format today includes a 30-minute live stream where each speaker will present their thoughts on reproducibility for 10 minutes. They've been given a completely open mandate, so I'm interested as you to hear what they've come up with on this topic. And after the live stream, our speakers will join you in the chat so we can engage directly with you, answering your questions and encouraging some lively debate and hearing your views on this topic as well. So I hope that all makes sense, and that's in way too much from me already. Let's get on with this talk. So Shea, I think you very kindly agreed to go first. So we're going to turn our cameras and microphones off, and we're going to let you take it away.
Okay. So we should hopefully be able to see this.
Yeah, we can.
Cool. Okay, yeah. So yeah, thank you for having me here, and happy to talk about reproducibility and sort of my take on it. So basically, most of my lab's work is sort of focused on looking at the interaction between the genes and environment and how this influences dementia pathogenesis. So a lot of the way I conceptualize reproducibility sort of comes from this computational research perspective. So basically, what do we mean by reproducible? So often we're sort of talking about this in, if we had two separate studies or more than two, is the significance or their p-values the same between studies? So we're evaluating replication effects against null hypothesis and null effect. And this is nice and simple. Does it replicate? Yes or no. But this doesn't really tell us about the effect direction. So it could be that two different studies find a significant effect, but they could be in opposite directions. So where we're looking at the effect size, so there's the original estimate within the 95% confidence interval of the effect size estimate from the replication study. Of course, once we start getting multiple studies together, we can then actually start looking at meta-analysis. So combining the original study that published a result along with multiple replication efforts to see is there a consistent effect size across multiple studies. And then we also just have this subjective assessment of did it replicate or not, based off our own internal logic and knowledge and a priori hypotheses. So after we read through the methods, are the methods similar? Are they using similar data sets? Are these results generalizable from one data set to another? So this is more of like a subjective measure of does it replicate. And sort of the issue that a lot of researchers have found is that many findings don't replicate. So this is an example from a recent preprint where they were looking at two research questions within ecology and evolutionary biology. And the first question was, to what extent is the growth of nested blue tits influenced by competition with siblings? And the second research question was how does grass cover influence eucalyptus sibling recruitment? And so this actually gave 246 different analysts exactly the same data set that had not been published before, asking the same questions and said, hey, go at it. What is the answer to these two research questions? And here we basically see the meta-analysis of those 246 different analyses. And the key thing here is there's a huge variability in what these individual researchers found using exactly the same data set with the same research question. And so you can see for this example looking at the blue tits, is that once you do the meta-analysis, there is this negative association, but there are a couple of studies here that actually found positive associations. And similarly, when we look at this eucalyptus question, the meta-analysis is actually no significant result, but we do see some individual studies with, again, negative associations and other studies with positive associations. And what they're really getting at here is this idea of this garden of forking paths, is that each analyst is coming to this data set with different a priori hypothesis, not necessarily a hypothesis, but a priori ways of analyzing this data. So even though you have the same question, there's different variables that you can use to answer it, different regression models or machine learning approaches that each individual person could be applying. And each path you take or each decision you make through this analytical journey can influence the end results that you get. And so this sort of highlighted this idea of this replication crisis, where people were seeing that results addressing the same kind of question were not consistent across many studies. And so an alternative way we can look at this is we can go to previous papers that have been published and try to replicate their findings. So this is an example from the Reproducibility project related to cancer biology. And they went through and identified 193 experiments from 53 papers, and they wanted to go through and replicate these findings. So they initially designed these 193 experiments and just immediately went into errors. But they couldn't actually replicate any of these findings based off the methods in their papers that they were analyzing. So part of this was, the data wasn't shared, the analyses reported weren't reported consistently. They need to actually get code from other researchers. Some of the reagents just were specific to a lab, and they had to get these delivered from the original lab. But I think one of the problems here is that when they recontacted the authors, only about half of the authors actually helped for this reproducibility. So out of these 193 experiments, they managed to initiate 87 of them, and then actually only completed 50 of these experiments. And out of these 50, the replication effect sizes for 85% of these studies were smaller, and the original positive results were half as likely to replicate than the original null results. So this is this idea of replication crisis. Can we actually trust the research that has been published? And this is becoming even more important because science is growing at an exponential rate. So this is the number of papers published since 1900 up to 2000. And the key thing here on the y-axis, this is a log scale. So essentially, every 12 years, the amount of research is doubling. So, yeah, another way to think about this is that 50% of all research has been published in the last 12 years. So if we're thinking about all these research that's been published, how much of this literature is actually reproducible? How much can we go back and trust? I think one question here is, well, the number of papers is doubling. So there's maybe an estimated 58 million papers. Most of these actually have a low impact on the field. So nearly 50% of these papers have actually never been cited. And it's really this, sort of like top 1% of papers that are highly cited and really drive the literature. So I think there's a question like, do we actually need to replicate every study? Maybe not, especially if they're not having an impact on the literature. And thinking more broadly in that, science is actually generally self-correcting. So people do try to replicate these more impactful studies. Maybe some of those results aren't replicated fully, but we have this sort of virtuous cycle where our science is continually being updated and results that are, don't meet this test of reproducibility will generally fall by the wayside. And this is our idea of the scientific method. We go through and generate our specific hypotheses, we design our study to answer that hypothesis. We go through and conduct our study, collect some data, choose a method that matches our question. So we're doing regression modeling, machine learning, using fancy new AI models. We interpret the results, and then we publish our findings, and we restart the cycle. So based on our previous findings, maybe we design a new study to answer a slightly new hypothesis. And this sort of replicates at a field-wide level, where multiple investigating groups are going through and reconducting these analyses. Well, not reconducting, but building on top of each other. The issue is that there are these threats to reproducible science, and part of this is like this incentive structure within science itself. So for me, running a lab, I need to get papers published to get funding to keep my people employed. So then I have this perverse incentive. I maybe only want to publish results that are significant rather than non-significant. I want to publish in high impact papers. And so this can sort of generate a culture where we are maybe cherry picking our findings. So when we specify a hypothesis, we fail to control for our preconceived biases. So maybe we're so embedded within the M-line hypothesis, we can't think about other ways that AD pathogenesis may be influenced. When we design our study, maybe we're only recruiting people based on the amount of funding we have, rather than choosing a method that fits the resources that are available. And this can lead to low statistical power and potentially results that are false positives. When we're collecting our data, again, maybe due to resource constraints, we are not collecting the data in the best way possible. So, Alzheimer's is a heterogeneous disease. Maybe we're doing a clinical diagnosis, and this is going to introduce variance into our analyses and reduce our statistical power further. When we analyze our data, we have to pick a method that is appropriate to what we're doing for the original question, and that suits the data we've collected. So, regression modeling works, but we could be doing these fancy AI and machine learning methods that are getting published in high impact papers because they're new and novel, but maybe the data we've collected actually isn't suitable for that kind of analysis. And maybe because we've collected so many variables that we can go through and start looking at p-hacking. So even though our primary hypothesis was not significant, maybe by chance we find another variable that is associated with our outcome, and that's something that we can go ahead and publish. Then we've got this idea of hypothesizing after we've collected our results, so hacking. And this is, we've found a significant result. It doesn't necessarily match our original hypothesis. So then we hypothesize based off our results. And I think this is pretty common within genetics, where we find the gene that's associated with a disease. We don't necessarily understand the biology, but we can find ways that sort of fits into our preconceived hypotheses. And then we come back to the idea of publication bias, where not all significant results are published. So at least within computational research, then, we've got this idea of these sort of 5 pillars that can lead to having a reproducible research. And it's about having the structure that underpins the research we conduct that leads to it being reproducible. And so the bedrock of this is having this end-to-end automated process. And this is where every step of our analysis is underpinned by a code base. So downloading the data, changing the variable, doing the regression, this is all embedded in code. This code itself is then version controlled. So it's not just that we have a little piece of code sitting somewhere on our desktop, but this code is then backed up onto, for example, GitHub, and every change we make to this code is recorded. We also have compute environments that are controlled. So software changes over time, and these changes can break code if we are not using the same compute environment. So you're sort of freezing the environment that you're working with, like the operating system and the versions of different packages. We also have the new tools to deliver programs. So this is like Taro in R or Jupyter Notebooks, where we just don't have a code script, but we can embed our results and the reasons why we're choosing a particular regression model, for example, or particular variables that go into a model is embedded along with the code. Of course, we also then need, really good documentation. So this is, where this, if we're making a new function, describing what the function does, what's the input and the outputs, what are the arguments, why have we chosen a particular default argument? And then also data, we have these ideas of these fair data principles, so it's findable, accessible, interoperability, and reusable. So the idea that we can find our data, it's publicly available, anyone can use it, and if they want to reproduce our results, they can download it. And this sort of leads into this idea of computational workflows. And there's a number of workflows like Targets is an R package, Nextflow is particularly being used a lot for RNA-seq. SnakeMaker is one that my lab uses as best of Python. Cromwell is another that's particularly used by the Broad Institute for whole genome sequencing. But the idea is that we can start off with there is no script. We're just clicking around in Excel, and there is no history to why we did our analysis of what variables were chosen. We're actually altering our original data rather than recording how that alteration was made. And to be honest, this is my very first paper. It was done in SPSS. It was all point and click. There is no reproducibility from my very first research paper that I made. But as I progressed in my PhD, I started learning a bit more of this computational research. So particularly I learned R. I started writing my own R scripts. But again, these R scripts just floated on my local machine. They were not backed up onto GitHub that was publicly available. And there was no commit history to why things changed within that R script. But once we upload these scripts to GitHub, we start doing our documentation. This is when we run into some idea of computational environments. When we start adding in additional infrastructure, we break down our very large script into subparts, one for data cleaning, one for analysis. We freeze the environments, we specify what the operating system is. And I think for most cases, this is probably a good place to end, right? For most research users. It's more when we go forward into computational environments where we're actually making software that is going to be used by other people. We're starting to be thinking about freezing environments and stuff. So anyway, the take-home message there is the amount of research being published is growing exponentially. And I think it probably is actually impossible to replicate everything, and I don't think we necessarily need to replicate everything. I think it then becomes more important to focus on training new PhD students, undergraduates to do basically conduct this reproducible research to improve the overall quality of our base research. And of course, then practicing open science. So yeah, happy to answer any questions or any ideas at this first. Thank you.
Thank you, Shea. You've given me so much to think about there. There were so many points that I just hadn't occurred to me. So, well, first of all, some of the stats in there about 50% of research papers never been cited. I didn't know that. I thought that's quite surprising to me. I pulled up lots of stats before we met, which I can reel off about just how low the reproducibility levels are amongst research, but that hadn't occurred to me. It also hadn't occurred to me about computer environments and software versions. I mean, do you genuinely get different results if you run the same analysis on two different versions of a software package?
Maybe not necessarily. I mean, maybe not necessarily the different results, but if you have random number generators in there, you're setting a seed. So that's consistent. That defines where that randomness starts. But it's more about dependencies, as software changes, like maybe some functions get deprecated, it just breaks the whole pipeline. So it's more around those kind of things. Yeah.
And also as well, I mean, it's not like older versions of software are easy to get hold of. I mean, that's it. Some are, but that's it. Once they become unsupported, you often just can't even get them anymore, can you?
Yeah. So I mean, I think that's where like Python and R is pretty good, because a lot of those old packages or old versions of packages are often archived, and you can get those right condas. Like having a conda environment sort of ensures that you have that frozen, and that's where I was talking earlier about having a frozen Docker environment. Like that Docker environment contains all those packages in there, so then anyone can basically take that environment and then just run your analysis within a new environment.
And so does that same count for when you publish in the? I mean, do you share all that as well with when you publish? Is all that information shared?
Yeah. So when we do snake pipelines, like each rule within that pipeline has a specific kind of environment that defines, what software is needed to run, that little piece of the analysis. Some of our publications are better at that than others.
Yeah.
But it's encouraging that kind of research culture within the lab that's important. And again, like I didn't learn any of this until I started my postdoc, so I'm still relatively new to this too.
Well, and so while I can see that's all made this more complicated, particularly as I'm guessing, as ever with these things, as computational research and machine learning plays a bigger role now, quite often we play catch up, don't we? We're so keen to get on and use the software that we don't fully think through all the implications, and so keeping pace with that. But at the same time, once you've got on top of that, this should help reproducibility, shouldn't it? Because that it kind of contributes towards you've got more transparency. You can document those things, and it's not software that somebody's. Although I'm guessing this still happens. You just write your own software.
Yeah, I mean, I'm much more of an applied researcher, so I take other people's software. And particularly during my postdoc, there was another postdoc with me. Like I write terrible code, he'll write beautiful code. But he'll take my terrible code, make it beautiful, then I would break his code. Again, like this nice virtuous cycle where, we work together nicely.
That's wonderful. Well, I'm not going to delay any further. We'll give a quick update, which is the Netherlands went ahead 1-0. And then there was a controversial decision where England were given a penalty and England scored the penalty. And so they're back to being 1-1 at 22 minutes in. So for anybody who's watching and who cares about that, it's 1-1. And Rebecca, we're gonna go over to you now.
Yes.
And then we'll be back in 10 minutes.
Lovely. So hello. So as Adam said, my name's Rebecca and I'm a PhD student here at the University of Cambridge. I'm not originally from a particularly academic background, and it's something that I found when I started getting into my PhD in this wonderful world of research. The more research I read, the more research I did, but I started to really think about whether we can trust our results, tweaking a tiny factor in a model or adding participants on, kind of going through and seeing the massive impact that can have on your findings. I just got interested in this question more and more. So today I want to talk a little bit about kind of this problem of non-replication and reproducibility, an explanation of some of the reasons why I think that it's so predominant, and then my solutions that I think can hopefully be implemented relatively easily into our everyday academic lives. So the problem itself, this was my kind of first introduction to this idea of trusting in research. There was the replication crisis kind of that happened in the early 2010s, where we really into the field of psychology started to doubt everything and question our lives. And part of this was because of this paper by Daryl Bem about feeling the future, about extrasensory perception, where he basically proved using research that was deemed up to code, he was published in a journal, everyone looked at it and said, yeah, this seems like great methodology, proved that people could see into the future. And you read kind of first-hand reports of scientists reading this paper for the first time and feeling physically sick as they battle with this idea that either they have to completely change their view of the world and time as we know it, or they have to admit that our scientific systems are so flawed that we can basically prove everything with what was counted at the time as good science. And this kind of prompted this big spiral of how much can we actually trust of the research that we've done. And one of the first studies I came across, which kind of showed that showed how important replication was actually in my college days, back at A-level, and I learned about this fantastic study by Meltzoff and Moore, where they looked at what age babies are able to imitate facial expressions. Wonderful little bit of research. And they found that, as you can see in the picture, even very young children could imitate faces. But then I later found out that was not taught on my A-level psychology class, that a lot of research had shown that actually that wasn't the case. And the only thing that could replicate was the baby pulling their tongue out, which they actually attributed to arousal, just the fact that they were excited that someone was interacting with them rather than an attempt to imitate. So I also think that some science that we still see as foundational, that is still being taught at A-levels, that is still being taught to students, in some cases hasn't replicated. And that's not just anecdotal proof. There are people who have gone away and tried to actively replicate different research from different journals, and overall found that 36% of research replicated, which is outrageous. And you know, going down to as low as 23% in the field of social psychology. And obviously this non-replication and these questionable research practices are a massive, massive problem. You know, we love the phrase in science that we're standing on the shoulders of giants, but we really want those giants to be pretty sturdy. And if we're basing all of what we're doing now, let's say this vastly increasing number of papers on research that doesn't replicate, or on research that's just incorrect, that we've p-hacked our way to, it means that we're basing our science of today on increasingly shaky ground. Which I would argue is ever so slightly problematic. So what's the explanation? How did we get here to this point where so many studies don't replicate it, and we're really questioning now this reproducibility of our science? And as Shea touched on, I think a big part of this is kind of questionable research practices. If you haven't come across this paper in Neuroskeptic in 2012 about the 9 circles of scientific hell, I highly recommend it. It's a great post, going from kind of mild things like overselling and post hoc storytelling, all the way to p-hacking, creative use of outliers, which I find a very funny phrase, to partial publication of data, non-publication of data, and then all the way at the end to kind of fraudulent data, which, you know, we have seen examples of. I think Deirdre Stapel being perhaps one of the most famous or infamous cases of just making data up. But I think most of us don't go that far. I think most of us stay at those lower levels, and we don't realize how much of an impact these tiny changes can have on the outcome of our data. Of, oh, well, I'll just rerun this and tweak this one variable. Oh, I'll just change this around slightly and no one will notice and it'll be fine. And we don't realize how much of an impact that actually has on our results. So in a paper by Leslie John in 2012 in the Association for Psychological Science, over 50% of researchers in the field of psychology admitted to deciding whether to continue data collection once they'd seen the results or not. And 27% admitted that at one point or another they'd said that an unexpected result had been expected right from the beginning. So like I said, I think a lot of us are guilty of some of these kind of minor misdemeanors in research that really can amplify non-replication and kind of false positives. There we go. And I think this is amplified further by the systems that we operate in. I think still to this day, you know, publications really do favor those magical significant results, and that not only incentivizes the publishing of those significant results, and that null results or results that perhaps people don't think are as interesting get lost in file drawers, which a lot of the time means that the one significant result is published while the 10 null results are lost forever. But I also think it means it incentivizes these questionable research practices to go p-hacking, to search for that significant result, knowing that those big papers are going to be the thing that makes your academic career. And like I say, as someone very early in my academic career, I certainly kind of feel the pressure of that, of making sure I publish and publish big, to build that foundation later on. And I think that can, in some cases, sadly incentivize these bad research practices, big or small. I promise fish are also relevant. So statistical power is something that I struggled to get my head around for a long time, until eventually someone used this analogy that really stuck with me, of a fishing net. And if you have a fishing net with a really fine mesh, it means that you're going to catch all the fish that come your way, even tiny fish you're going to catch in your fine net. And that's the same as when we have something with high statistical power. We're going to catch lots and lots of effect sizes, even the teeny tiny ones, because we're powered to do so. However, if we have low statistical power, and we have a really, really large mesh with many, many holes in it, then a lot of the fish are going to slip through until the only fish that are caught are really, really big, strange ones that probably shouldn't be there in the first place. And I think statistical power, again, isn't necessarily taught in this way. We know that bigger is better. Like, it's one of the bread and butter things with my students when I ask them what could we do to improve the study, increase the sample size. But I think very few people can verbalize why it's important to increase the sample size. Why is bigger better? Is it better in all cases? And I think studies with low statistical power, as they often get these artificially inflated p-values and significant results that can lead us down a bit of a wrong path, a little bit of a red herring, if you will. And obviously another advantage of kind of these bigger sample sizes is the diversity of the sample. I think a lot of studies don't replicate because they're done in a very specific group. We try and replicate it in another group, and we don't see the same results. Young versus old, different racial groups. So I think it's increasingly important, and we see it's increasingly important to have larger sample sizes, not only for that statistical power, but also to increase the diversity of our sample. So that's some of the reasons why I think that non-replication and reproducibility crises may be going on, perhaps not so much now. And for me, the solution, I wanted to aim for things that I think can be implemented on a day-to-day. You could go away and implement tomorrow if you wanted. And for me, the biggest one of these is OSF, which is the Open Science Framework. If you hadn't heard of it, I fully encourage you to go and explore it. On the Open Science Framework, you can pre-register your research, which means you put up the introduction, the methods, your hypotheses, there for everyone to see. And that means that when you do eventually publish a study, or if any research comes out of it, you can cite back to this pre-registration and say, this is what I intended to do, and this is what I did. And that allows people to compare the two and see, did you p-hack? Did you change your hypotheses? Have you started playing around with all those little variables that we mentioned earlier? Have you changed your hypothesis completely? And I think a lot of people get nervous about this because they're really worried that they're gonna tie their hands, and that if they find something interesting or they realize an analysis technique isn't working, but they've pre-registered it, that they're stuck and that's it. And I would like to say that I really don't think that's true at all. To me, at least, as someone who's pre-registered a couple of studies now, it's not so much that pre-registration stops you from changing your plans. It's that if you do change your plans, you have to explain why. And if you're doing good science, that shouldn't be a problem, because there should be a reasonable explanation of why you've changed plans. Like I say, I'm doing a lot of exploratory stuff at the minute. So I've pre-registered just that this is my hypothesis. I'm not quite sure how I'm going to do it yet, but these are the basic bare bones of how I'm going to make the decisions along the way. And pre-registrations can be very strict, or they can be, very narrative and open. So I really encourage having a look around those. With that, there's also, of course, registered reports. A lot of journals do these now, right up to Nature, where you submit an introduction and a method section, and they will choose to accept or reject your paper based on that, with no bearing on the results at all, which I think is fantastic for incentivizing that good science rather than significant results. It stops us chasing after those magical p equals 0.05s. And again, it really puts all the work at the beginning of a project, which can feel like a lot of work, but it also means it speeds up the end really significantly. My first project, I think I analyzed in a day because I had all the pipelines ready to go. I had the paper ready to go. It was literally just hit run on the analysis. So it changes the workload slightly, but I don't think it actually increases the workload any. Another note on kind of, I said a lot of papers get put in, the file drawer effect and publication bias. And I think another way we can combat that as researchers is using preprint servers like bioRxiv and medRxiv. There's really no excuse for a null result to be stuck in a bottom drawer anymore. You don't have to get it through peer reviewers. You can put it up for everyone to see as a preprint, and share that around, reference it in studies. And I think that's become increasingly popular, especially over the COVID-19 pandemic, with the speed that literature was coming out, and journals just couldn't keep up. And as well as, open science, I think open data, open materials, open code, we've already talked about, are really important. I think a lot of the kind of backlash that I see to this is that people are worried that they'll get caught doing something wrong. They'll put their code out there and someone will see it and go, oh, this is incorrect. And to that, I say, good, that's the point, right? The point is, the reason we're putting all this out there is to improve the quality of our science. So if you put it out there and someone notices a mistake, that is exactly what it is designed for. And I think part of kind of all of this open science is also opening up communication and being honest with ourselves and with other scientists that we are going to make mistakes. You know, we're humans, we're going to analyze something in an incorrect way, we're going to engage in some questionable research practice where we didn't think about it at the time, but now maybe it's a bit of a gray area, all this kind of stuff. And I think opening up communication, healthy communication about that, where we can acknowledge it and talk about it freely and openly, will hopefully reduce it even more and reduce the guilt associated with things like this, of being wrong. What happens if I write something in my pre-registration then realize it's untrue? What happens if I make my code open source and then someone notices a mistake? That's the point. We're all learning. We're all scientists. We're not perfect, and neither is our research. And I think being open and transparent about that will ultimately make it better. And my hope would be that by kind of combining all these together, we create a much more solid foundation to our science, where we can trust our results, both our own and everyone else's, to create that stronger foundation on which to build the next steps. And that's all I have to say. So I'm also going to stop sharing, and I'm very happy to answer any questions or have some discussion.
Thank you, Rebecca. Honestly, that was a great presentation. I don't think anybody watching will believe that you're in your second year of your PhD, third. It's crazy. Third year now. Because you know, that presentation was at a much higher, not much higher level. It was really good. But what I'm really interested to know is how did you find that all out? I mean, where does this come from? I mean, you've got this very mature approach to understanding about all these different approaches to doing your analysis, to pre-registering, and I'm not convinced that every PhD student I come across has got that same level of knowledge. So what makes you special? How did you gather that knowledge? How do you know this? Is this just because, you know, Cambridge is great at teaching this, or is this because you've gone out and found this out for yourself? Have you just got a great supervisor? Where does that come from?
I think a bit of everything. So I taught once I did kind of my A-level psychology course, and I taught it for a little bit, and the more I taught it, the more it annoyed me. Kind of teaching kind of statistics and what p-values were and all this kind of stuff. And you teach the textbook answers, which was, you know, we choose p-value equals 0.05 as our significance level because it offers a good balance between our chance of false positives and false negatives. And then I tell them the real answer, which was that we had to kind of pick a value, and this seemed like a pretty good one to go with. And so I think part of it was kind of learning more about the syllabus that I'd been taught so much, and then realizing just how much of it was not necessarily wrong, but just not quite right. It missed a bit of nuance, which I suppose you have to do at some point. And then I think when I got to my PhD was when I started getting really interested in statistics, and kind of Bayesian statistics and versus frequentist statistics, and how that can have an impact on the research that we're doing. And we have a fantastic program leader at the Cognition and Brain Sciences unit called Amy Orban, who I think is a big pioneer of open science and open research, who did a course for us when we first started about the replication crisis, about pre-registration, open access, open code. And I think she did a fantastic job of introducing a lot of these concepts to us and giving us just the confidence to. So in my lab, I know a few people pre-register their research, but it's not kind of a bread and butter thing. So it just gave me the confidence to say to my supervisor, you know, I want to pre-register my research. This is something I really want to do. And the minute I said that, he was very supportive of doing it. And like I said, I found it a really rewarding process, especially as I think an early academic, of having everything laid out before I do the analysis. Makes everything feel much more concrete to me, as opposed to kind of playing around with stuff. So yeah, I have to give credit to some fantastic teaching, I think, at the unit, which really opened the door for me.
And thanks, Rebecca. And where do you sit on this, Shea? Do you pre-register your studies? Do you encourage it? And what kind of what? I mean, obviously you're more senior in the institution where you are now. How much is reproducibility talked about within your lab?
Yes, I mean, I haven't pre-registered any of my studies, and I tend to more focus on the technical side, you know, like having the code open access, open source, and using open data that is as open as possible. Yeah, not all data is open because patient health data. But what I like to do for my trainees when they come in is get them to write a statistical analysis plan. it's not the same as peer registering, but I said, you're writing up your background, tell me what your hypothesis is, how you're going to, what's the method you're going to use. This isn't so much for open science per se, but it's also to, not get lost down that garden of forking paths, right? Because it's very easy to, you want to perfect your analysis. Like I did this during my PhD, like I said, when you mix the packed models, it's like tweaking every little thing in the model to get the perfect model. There is no perfect model. So just taking a step back and saying, what is your objective and how does your analytical method fit into that objective? And not trying to stray too far from that. I think you still can stray from it. But as Rebecca was saying, you've got to define why you're doing that. So I think it just brings a bit more of an honest critique into the research that we're doing.
It's that informed decision making, isn't it? I completely agree. I mean, I apply that in so many other areas. It's not to say that this is wrong. It's just that you've got to be able to explain properly why you're doing something. So, well, let's pick up on us. I got some stats, and I haven't gone to all this trouble to research these stats and not spout them. So we're still 1-1, incidentally. A survey conducted by Nature in 2016 revealed that 70% of researchers have tried and failed to reproduce other scientists' experiments, and more than half have failed to even reproduce their own experiments. Does that surprise you? Not either of you?
70%? Yes and no.
Tried to reproduce somebody else's. Have you ever tried to reproduce some other people's research?
Yeah, I mean,
you both have.
There was one paper, looking at the effect of ApoE on Alzheimer's across different genetic ancestry groups. It was a paper from 1997 that everyone cited, and I don't like citing papers that are more than 10 years old. It's just my,
No, I think that's the standard these days, isn't it? Unless,
right.
It's the original,
well,
the Hardy paper.
Right, so I thought, we've got bigger data sets now, let's try to replicate this, and I couldn't replicate his original findings. But then I was talking to one of my colleagues, I said, I've got a bigger data set than you, let me try this, and he did replicate them. So it's, getting back, even though you've got different data sets, each data set itself has its own idiosyncrasies. What's the age breakup? Is it population-based? Is it clinical? All these things are going to affect results. So that's why I think that meta-analysis at the start is interesting, because it's really a consistency of effect across multiple studies rather than relying on one single study to define the ground truth.
That's a really good point, isn't it? I mean, it doesn't. I mean, it matters that it's not reproducible, but as long as everything isn't hinged on one single pivotal. Which actually leads on to another interesting statistic, which a report published by Friedman in 2015 estimated that irreproducible preclinical research cost the US $28 billion annually, apparently as well. And we'll just have one more, and then I'll ask you a question, which is in cancer research, a study by Begley and Ellis found that 11% of preclinical cancer studies only 11% could be reproduced. So it's interesting, but does that hold back the scientific discovery? I mean, Rebecca, you I think have argued that it would in some areas. You've got to be able to trust what you do. But let me move on to some questions, which is I'm going to ask one to Shea first of all. How do you see the role of statistical methods in improving How do you see the role of statistical methods in improving reproducibility in genetic epidemiology?
Yeah, I think genome-wide association studies is one of the successes of replication, right? Because back in the 90s, it was all candidate gene studies. You pick out your favorite gene, find a genetic variant in that gene. Is it associated with Alzheimer's? Is it associated with Parkinson's disease? And basically nothing replicated. I think from that whole candidate gene era, maybe there's one gene that has not been replicated in genome-wide association studies. The whole idea of the GWAS is that we're looking at every single variant across the whole genome with your trait of interest, and using a really stringent p-value cutoff to account for that multiple testing burden. If there's 20,000 genes, by chance 5% of those are going to be false positives. So yeah, I mean, I think within genetic epidemiology, I think we're in a good spot. The issue now is we're moving into like this multi-omics space. Where we're bringing, proteomics, transcriptomics, metabolomics, integrating all these data sets together. And again, this is being done in a much more hypothesis-free way. So again, there's this issue of, we find something interesting and then we tell a story about it. But
is that okay then for that to be temporal? That you just know that the continued addition of extra data, more data, it's inevitable that results won't necessarily be reproduced because the more you add in, the more factors come into play.
Yeah, and that's sort of what I was getting at. This idea, science is self-correcting. Yes, we are going to waste resources, but we're going to do that anyway. I think it's making sure we're not wasting too much, and that comes like having this solid foundation of training around reproducible research, and having this data sets open so you can justify why you've done a particular analysis in a given way, and if your data set's open, then other people can try different things. And it's like looking for that consistency and effect across multiple analyses.
And thanks, Shea. Rebecca, you already answered my questions because I had like primary challenges to reproducibility. How do you think ECRs can contribute? And I think you really did well in covering all of those topics. So I'm gonna ask. I'll come back to you with one question, and then I'm gonna give Shea a pop at this as well, which is how can journals and funding agencies better support reproducibility in scientific research? Let's go for you, Rebecca, first.
Yeah, I think, like I say, I think registered reports are a great start. I think taking the focus generally off results as being the end game and putting it onto studies that are creative and have sound methods, regardless of what the results are, I would hope would incentivize people to engage in good science rather than aim for good results. But I think that you can also shift at kind of a smaller research culture level. I still talk to a lot of people who are like, it feels like the amount of praise that I'm given is dependent not on how hard I work, but on whether my result is significant or not. So I think that can also trickle through kind of at a lower level. And I think opening up the peer review process as well is always helpful. I think, again, opening up conversation and making those processes more transparent, I think, can never be a bad thing.
Well, if you're interested in peer review, our session at lunchtime today was on peer review, and I kind of sat there thinking, okay, I've decided I want all peer review feedback now to come in the form of a video. I want the person who's doing the peer review to actually video themselves giving the feedback so they can properly articulate themselves, be accountable for what they're saying. And I think we know that you just won't necessarily say face-to-face something that you would write down. I quite like. Yeah. You should make a video.
And I think you can have really interesting conversations, right? If you notice something in someone's methods where you're like, I'm not sure about that, I think you can have really interesting conversations about why they've done it that way and how you would have done it, and it becomes a little bit more kind of collaborative than maybe it is at the minute.
Make it a conversation rather than a kind of transactional messaging system. Shea, what can I get your view on this? How can funding agencies and journals better support reproducibility?
Yeah, I mean, definitely as Rebecca was saying, like, having these register reports, I think that would help. Because like, even though we say, we want to publish negative results, that takes time and resources. Like, even if we're just going into a preprint server, it's the time it takes to write that paper up. I could spend that writing a paper with a significant result that's actually going to benefit my career more than a negative result. So again, we've got that incentive that I do need to get funding and money, and so it's more around those incentives. I mean,
sorry, carry on. No. I'm just thought of a question.
Yeah, I mean, from the funding side of things, I think we're moving a bit more towards this, like data sharing plans, like NIH is now requiring this. Like, how we're actually going to share our data for other researchers to use, they are requiring that. I think, again, that opens things up a lot more.
It's tricky, isn't it? Because they're more likely to fund things that are progress, like that they see as having an outcome. Not that I don't know how many people have asked for money as part of their last grant application to also include some reproducing previous results and what kind of response that got, or how that went through peer review. I'd be interested to know.
Yeah, so that is now expected to be included in there. Like if we are generating new data, we are expected to provide that data to make it publicly available and also then request funding for that. But that's then limited within if we have a 500.
But that's to help the next person, isn't it? I suppose, not allow you. So I guess the next people to follow you will benefit from that. And yes. I wonder if your quote about citations from before. I wonder if negative results are more cited. That whole actually whether you getting something didn't work. I wonder whether you get more citations from a negative results paper. I know you don't want people don't like to them, and you can't even get them published necessarily. But I bet they get cited more. It's just a hunch. I don't know. I need to go and research that question. Thank you so much, Shea Andrews, Dr. Shea Andrews and Rebecca Williams. You've been brilliant. Both your talks were fascinating, and I'm sure if anybody, we didn't get so many people joining us live this evening, but I hope you will watch this on chat, on Watchback. And please do, even though you couldn't be here in person today, do contribute to the discussion afterwards and make your comments. Shea and Rebecca are both available in the platform as well and have messaging enabled, so you can drop them a line if you've got any questions. And Shea, Rebecca might be looking for a job in some time, so it sounds like Shea's lab in California might be a nice place to work, maybe.
Always be networking. Always be networking.
Exactly. I've got my positions.
Well, thank you very much, Shea. I will see you in a couple of weeks' time at the AAIC. I don't know if Rebecca, you're not there this time. No, sadly.
Not this time.
But we're going to join you in the chat now, and we'll look forward to taking any questions you've got and continuing this conversation. Thank you very much, everybody.
Thanks for having us.
Thank you.